Thank you, Neil, for inviting me, first of all. As you were saying, I'm Sabrina. I'm doing a PhD here in London at UCL, and I'm in the Department of Computer Science. My bachelor and master is physics. I studied it back in Italy, and this is my second year of PhD. The main project of my thesis is systemic risk in decentralized finance and centralized finance. This is actually my first paper during the PhD, so I'm very proud to present it. Thank you for your invitation again. So this is a paper with some professors from University College London, like Professor Bartolucci, that is my supervisor, some from University of Cagliari in Italy, and others from Brunel University, that is another university here in London. And the main goal of this paper is to analyze the code behind the decentralized applications in order to see if there are any vulnerabilities of the code that could be exploited by hackers in order to steal some tokens, and how to prevent them to have a safer ecosystem. Oh, I can't. Okay. So we all know that decentralized finance is gaining a lot of interest in the past years. We have more than 40 billions of USD that are locked in crypto protocols, and we have more than 100 million wallets that are active worldwide. And even if it's still a small portion compared to the traditional finance importance in the market, it's gaining more and more interest from investors and users. The DeFi ecosystem has a lot of services. Like we have, for example, Bitcoin, that is the first one and probably the most famous, the token of Ethereum. But all of these services works always in the same way. They are built with these bricks that are a smart contract. A smart contract is a digital version of the legal contract. Basically, it's a piece of code that is written by a developer and deployed on a chain, and has some inputs, some function inside, and an output. Now, inside the functions, there are some conditions that are embedded inside, and if these conditions are met, then the smart contract will automatically execute the code and will give in output some values or parameters. Now, the smart contract have all the best features of blockchain. So they are decentralized. We don't have a central authority that checks on them. And they once that they are deployed, they cannot be changed by anyone. But the problem is that these good features, if we are in presence of a malicious attackers, or if there's a bug inside the code, could be a potential risk. Imagine that we have a bug inside the code of the smart contract, and once it's online on the chain, users start to interact with it. This bug could bring to loss of tokens, or could be spread across the service that we are using, jeopardizing the entire outcome that we want. So there are good things, but there are this technical risk that needs to be taken into account. Contracts usually perform a single task that is simple, like transferring a token, for example. But when we combine different contracts together, we have the decentralized application. It is basically a collection of contracts that has a purpose or a specific task and is deployed on one or more chains. Now, how does it work? We have here, for example, the example of Aave. Aave is Ethereum-based and belongs to the DeFi category that has more than 100 contracts. This on the left is a scheme of how the decentralized applications work. We have different contracts. Inside every contract, we have functions, and these functions call other contract. In order to they have some inputs, they process these inputs if the conditions are met, and the outcome is given as an input to another contract. And when this chain of calls is over, the decentralized applications perform the task that we want. Now, these functions, the call of these functions and the functions being performed has a cost that is called the gas fees, the gas consumption. Here, for example, we have Aave, that is a lending protocol. So it gives loans, giving some collateral, it has some loans that has a balance of more than 100 billions of USD. This is, of course, not the only DApp that has this huge balance, and that's why understanding if there are vulnerabilities inside is important, because if someone has bad intention and attacks a DApp that has this big balance, could jeopardize the entire DeFi ecosystem.
Can I ask a question?
Sure.
So in your definition for decentralized applications,
Yeah.
if the smart contract, if the application only has one smart contract, it's still decentralized application, or like or you want it to have more than one?
Yeah, we consider decentralized applications that have more than one contract. The smallest one that we consider has 4 contracts, but we consider like dApps that have a relevant balance, so they have a like not one contract in order to perform more complex tasks.
I see. But this because when you have one contract, you see it as centralized in the sense of contracts that you have on.
No, because we are interested in the way that contracts call each other in the chain of calls. So if we have just one contract, we don't have the information of how the information spread across the decentralized application, because we are interested in the flow of information. So
Makes
thank
sense.
you.
Thanks.
The hacks in the DeFi ecosystem are quite common. The point is that dApps, in the way that they are developed, they are not immune to security breaches or hacking attempts, because when like the DeFi environment is relatively new. So the developers, some are self-taught, or some like are just deploying something that they're interested in. And if there are some rules that are followed in the traditional software services, these rules are not defined in the DeFi ecosystem. So these developers do not have some good rules to follow in order to deploy them. And it's not said that they are making a good job. In addition to that, we know that there are many works in the literature that studies the vulnerability inside the smart contract, so as a single entity. But there's no literature of a systemic risk of what happens when we link multiple smart contracts together. So the smart contracts are always checked as a single entity, and they're always checked if there's a vulnerability or a bug of the code inside it, but like when it's not used with many contracts linked with each other. So exploiting DeFi projects for these reasons is extremely easy. And it has a low risk because of the anonymous environment that we are in, and has high reward opportunity. For example, we have like this is like an example of toy DApp that is a DApp that simulates what happens during an auction. So we have some participants that make some bids. There are some items that need to be sold, and these items are assigned to the people that make the biggest bid. Well, there are many works that do very good taxonomy of vulnerability. Here we just present 2 of them that are vulnerability to time dependence and vulnerability to reentrancy. But there are many studies that have a classification of the different vulnerabilities that are the most present. We have 4 contracts. So item is the contract that has the ownership of the items that need to be sold. Then we have a participant that has the information of who is participating and the bid that they make. Auction, that is the one that manages the actual auction, so the compares the bid that gives the item to the participant who is winning. And Vault is the one that has the ownership of the items until they are sold. Now, imagine that we have lock release that is vulnerable to time dependency. If someone knew that there's this vulnerability, it could easily exploit this vulnerability in order to unlock the item before it is actually sold to anyone. Or like return unsuccessful bids and place bids that are vulnerable to re-entrancy. It can someone could easily exploit this vulnerability in order to take advantage of those bids that are unsuccessful and transfer the tokens to its own account. So we have like it's easy and has a low risk if we know where to look. Let's say that. There have been many hacks in the history of DeFi. First, like we remember DAO hack in 2016. That an attacker attacked the split DAO, the function split DAO, that was actually vulnerable, that had a vulnerability of reentrancy, and managed to transfer more than 50 millions of USD in its account. Or like another one, a Ronin network hack, more than 600 millions. So we are in presence of a huge problem. And the crypto crime report states that in 2022 alone, more than 3 billions of USD were stolen from DeFi protocols. So it's a huge problem that we have to take into account if we want to invest, interact, or if we want just to study with these platforms. This is the distribution of how the cryptocurrencies were stolen in the past years. As we can see that from 2020, the DeFi protocols gained more and more attention. So it becoming the major source of the major source of victims in 2022, that is the pink bar. So these 3 billions of USD were like 82% of all the cryptocurrencies that were stolen. And this is exactly the framework where our paper is. We have decentralized application. They have a huge balance. There are a lot of tokens that are locked inside the smart contract. And they are built by developers that maybe are not that experienced or they do not have rules to follow. So our research questions are, first of all, if there is a common development patterns behind these decentralized applications. So if they are all developed in a similar way, or if developers do not share knowledge, so they are all different. Then we ask if there are any topological properties in common, how these relate to security risk. And if the DApps are vulnerable to targeted attacks, or they are quite resilient and they are not easy to be exploited. In this paper, we leverage on complex network tool, but given that the problem is an engineering problem, in the paper we use this terminology that is complex network-driven software engineering approach. Okay, so we can start from describing the data set. The majority of contracts are deployed in Solidity, that is a language programming, high level. And they are usually in an open source fashion on GitHub. So if we go on GitHub and we look for Aave, that is the DApp I presented before, we have a folder that is contract, and inside we have all the data that we need. So all the contracts and the functions inside, and how is the call between functions. These contracts, they are all made independently one of each other. So they are all made in isolation, and no one is actually looking at a systemic risk of them. So we can all find it defined in different files. In order to extract this data set, we use MindedApp. That is a tool that was introduced in 2023 by Giacomo Iba. That is the reference here, number 5. And MindedApp works with Solidity contract. it goes through the contract. So for example, here, panel A on the left, it goes through the contract and it identifies the AST of the contract. So he's able to build a hierarchical structure of this contract. It recognizes the dependencies, the libraries, the external call. And from this AST, he reconstructs the logic of the calls. So he breaks down the code in tokens and then reconstructs the calls that are happening inside and gives in output the information that we need about contracts and functions. We use this tool on 66 DApps, and this is how our dataset is distributed. We have the majority of the DApps that are Ethereum based, that is the green color, and are 51 out of 66. But I have to specify that like 10 of these DApp are actually cross chains. So they're not just Ethereum, but here we label it as Ethereum for simplicity. But we focus on DeFi category. And that's because in the crime report 2023, it states that the majority of attacks that are happening are focused on the DeFi services. So they do not care a lot about games or marketplaces or others, but they all attack the DeFi services. And that's why our dataset is built like this. We use the tool minded up on these 66 DApps. And for each one of these, we have in outcome a CSV file that is like this. Now, imagine that the one below is the DApp that we are considering. We know that there are 3 contracts. For example, contract A, that is the contract that makes the call and is in the column source contract. Then we have function 1, that is the function that actually makes the call and is in the column source function. And we have the contract B, that is the contract that is called, that is in the column target contract. So this is what the tool gives in output. Now, we are interested in how a bug can spread in the DApp and if the DApp is resilient to the flow of bugs. So we are interested in knowing how contracts interact within each other and an even higher level of resolution, that is how functions interact within each other. So we are both interested in the contract network and in the functions network. And this replies to your question before that was like why we take in account more than one contract, because we need to, like, our purpose is to study the flow of information within contracts.
So I have a question. I'm not familiar. So in terms of gas units, because for example, you can have one contract with 3 functions that can do the identical kind of result as having 2 contracts, which just kind of share some of the functions and split between them. And my question is, like, for example, in terms of like the mechanism design, what is the cost of having 2 contracts instead of 1? Because you can have 2 contracts that one is calling to the other and then run the function, or you can do everything in 1 contract. So the question is if it's costly, and also what is the added value of splitting your contract to 2 instead of having 1?
Okay, the thing that has a cost is the function, when the function calls something. So if we have 1 contract with all the functions inside, it doesn't change from the situation where we have many contracts with the same functions, with the same number of functions, because the thing that has a cost is the function that makes a call. It doesn't matter if it's inside the same contract or in another contract. And that is the transaction that has a fee. So from a energetic perspective, it doesn't make a difference to have 1 contract with many functions or many contracts with few functions inside. It has it changes from an engineering perspective, because dividing functions in different contracts means that we are dividing responsibilities and tasks across different contracts. So if a contract is bugged or is disrupted or doesn't work anymore for any reason, it's more or less self-contained, and this is actually one of the results of the contract network. But if we have one contract with like many functions inside, if one of that function stops working, it could affect the entire contract. And this is actually one of the results that we have, that these DApps are built in such a way to share responsibilities across different contracts.
I see. Okay, makes sense. And one small question is, when you look on contract networks, you mentioned that one decentralized application can be in different chains.
Mm-hmm.
I see it, but there is something else that, for example, you have Uniswap, that some other decentralized application like Ava or whatever use Uniswap as a smart contract that they use in their smart contract network, but Uniswap has no connection to them. So in some sense, like some people use other smart contracts that are out from their application because they want to use information or price or cards or whatever. So how you treat these cases?
We treat this case introducing a contract that we call non-contract, because it is an external dependency. So we consider the contract inside the chain, but all the calls to contracts outside the chain, we label them like none in order to say that they are external.
Okay, makes sense. Perfect. Thank you.
Thank you. If you have other questions, I mean, feel free to. Okay, so we have the information about contract A, contract B, and function, and we want to reconstruct the chain of calls. Now, for the contract network, it's straightforward because we have all the information available. So we take the source. Can you see my mouse? Okay, so we have the source contract column and the target contract column, and we can just build the agency metrics of the network. So on the source, on the rows, source contract, on the columns, target contract. Now the matrix has 0 if they are not connected, has 1 if the call is made just once, or can be any natural number if the call is made multiple times. Now, from this agency metrics, we build the network of contracts, and this network are weighted because of the possibility of multiple calls from the same contract to the same contract, and they are directed because there's no reason why they should be symmetric. The chain of calls should be symmetric. So we have 66 contracts network, 1 for each DApp. For the function network, it's a bit different. It's not that straightforward because the function, when makes a call, calls the entire contract. It doesn't call the single function. So we have to infer the network of function calls. How do we do that? We have the information of the source function and the target contract. And in graph theory, this is called bipartite network that is described by the bi-agency matrix, because we have 2 different layers, meaning that we have nodes of 2 different species that are the functions and the contracts. And we want to project the information from these 2 layers to the only layer of functions. Now, this is extremely common in graph theory, and it's called the probabilistic spreading approach. And it's a probabilistic method that reconstructed the most likely network of functions. Now, imagine that we have 5 functions, F1 to F5, that is the top row, and we have 3 contracts, C1 to 3, and we are interested in the link F3 to F4. Now, we know that F3, for example, has to go to the contract layer and then back to the function layer. And from F3, a bit of information, in this case, can just go to C2 with a weight of 1. Then once it is in C2, it has to go back to the layer of the functions, but it can go back to F4 with a weight of 4, F3 with a weight of 1, and F1 with a weight of 2. So the probability that this bit of information in C2 goes back to F4 is given by 4, basically the paths multiplied by the probability. So in this case, 4 plus 1 plus 2. That is the number of possible paths for the probability to go through that path. So in this case, we have 0.57, that is the probability of going from F3 to F4. Now, it's important that we are we are considering the hidden interactions between functions, because we are inferring the most likely network of function calls, because we don't have actually the information of how the functions call each other. Now, in formula, this is described by the top row over here. We have that the probability that a bit of information goes from function 1 to function 2 in the layer. There's a question. Yeah. Like the question is, if I study if the weights have a different compared to the unweighted approach. Yes. So okay. So retaining the information of the weight here is extremely important, because when we have the okay, I'm sorry. When we have the function that calls the contract, the information of the weight means that we are calling that contract more and more times. That from an engineering perspective means that we have a higher gas consumption, a higher fees. So we consider even the network where here it's unweighted. But for our purpose, it's meaningless, because we want to retain the information of how expensive that call is. So retaining this information of the weight 4, 1, 2 means that we know that here in this path, we have a higher gas fees compared to this path and compared to this. So we study the unweighted networks as well, but they are not relevant for what we are looking at. So is it clear or? Okay. So I go on, but feel free to ask. So a bit of information goes from a function 1 to a function 2 in the same layer, going first from F1 to a generic contract C in the contract layer, and then back to F2, summed for all the possible contract. And if we write it explicitly, it basically follows the connection pattern of the matrix. So it is multiplied by the weight of the matrix. And the reason is that like the weight for us means the gas consumption. So it's not it's an information that we want to keep. It's important. Now, this defines the network of functions. And for each DApp, we have a network of functions. Given that this approach is probabilistic, we then filter the network with this filtering method that is introduced in the reference 7 here, and is called a disparity filter. Now, the disparity filter compares our network with a null model and test the estimated links in our network with a null model, retaining just the links that are considering statistical significant compared to a p-value. So this filter filters the actual backbone of our network, so we do not consider the noise anymore. but we just like retain the statistical significant links between functions. We choose these filters in particular because this filter keeps the information of the weight distribution at all scales. And we are indeed interested in the weight because it means gas consumption. And this characteristic of this filter is that at each scale, it keeps like it takes care of saving the weight distribution. So it's perfect for our case, basically. So we filter the networks. They are we keep the part that is statistically significant, and we have finally 66 network of contracts and 66 network of functions that we can now analyze with network tools. I start now with the contract network and then I go to functions network. This is the contract network for Aave. Now, what happens here? We have that each node is a contract, and a link between nodes means that the contract is calling another one. Now, the node is blue if it has a self loop and is black otherwise, and the width of the border of these nodes means how many times that self loop is done. So how many times the contract call itself. So for example, here we have this contract to call itself many, many times. And the contract over here does one time. So it has some input, it makes some tasks inside the contract, and the output of that contract is given back as an input. And we actually have here, as I was saying before, the non-contract. The non-contract is the external dependencies, the one that we were saying before. So we see that there is some kind of there are some links, but many of them point to this none. So they are an external dependency. Now, the thing that emerges from this network is that the contracts are all self-sufficient. There is a lot of interactions with themselves, and they do not interact between them. So we ask if this is a common thing between DApps or it's just Aave. So we plot the distribution of the degree, so the number of links for each node. And we have the degree is like 2 to 3, very low. The density, so the amount of connection compared to the amount of possible connection, maximum possible connection that we could have, is again very low. And this is the ratio of self-loops. We are saying that 33 networks out of 66, that is basically half of our data set, have at least 60% of the nodes that are connected just with self-loops. We are saying basically that all our networks are is isolated nodes that interact just with themselves. And the reason, from an engineering perspective, is that there is a high level of interdependence and there is a very minimal intercontract dependencies. And one of the reasons that could explain why the developers made this choice is to improve security, for sure, because if there's a bug or if there's a vulnerability, we are reducing the risk of the chain failure, because if just one contract has a bug, it cannot spread across contracts in this way. And they are all self-sufficient, so they do not need external calls or external parameters. And this is, of course, very useful for the potential scalability of the entire ecosystem. And we saw we studied all the networks, and we saw that the contracts that interacted were the ones that were similar by functionality. So this is already a big result, because the developers didn't know how to, there were no rules that were stating that the contracts need to be developed independently. But it's something that is self-emerging from all DApps, no matter the use case or no matter the chain that they are developed on. So now I go to the functions network. And so a higher resolution of the problem. And as you can see here, it's a bit different. we have, this is always for Aave, and we have that there are many disconnected components around here, and there's one largest connected component that is the one that I'm highlighting here. Now, the previous information that contracts just call each other, just call itself, the same contract call itself, here translates in the fact that these functions here, these disconnected components, are functions defined all in the same contract. So what was happening before in the blue nodes isolated here means that we have these functions that they are grouped here in these connected components, that they are all defined in the same contract. We analyzed the code of these components, and we found out that these are secondary functionality of the DApp. So they are not the core component, and they were added, in some case, they were added later at the DApp for adding secondary functionality that were not that important. But of course, the most important thing is the connected component here, the largest one, that has the core functionality of the DApp inside. And this is the only case where functions that were defined in different contracts interact. So what we had here, like this part where we had a sharing of information here, is basically this part here, if we zoom in and we look at the functions. Here, that is the largest component. We have functions like set interest rate or set implementation pool, so core functions that are fundamental for the life of the DApp itself. And again, we ask if it's a common thing or it's just Aave, and it's of course a common thing even in this case. We have a higher degree, a higher density, so the networks are more connected, and the ratio of self-loops is extremely lower compared to the other case. We have that 65 networks out of 66 have just 15% of nodes that are connected just with self-loops. Now, what does it mean from an engineering perspective? It means that there are some tasks that are secondary and not core, that do not interact with the other functions, and they are defined in single contract. But then we have multiple contracts that interact within them, that are the core part, where the most important tasks of the DApp are computed. From now on, we focus on the functions network because they are the one that from a network perspective are more interesting. And this is and we study some metrics of the network. This is, for example, token set. So token set is a DApp that is Ethereum-based and belongs to DeFi category. And here we have the frequency of function calls, and we see that 47 function call 1 to 4 smart contracts. So as I was saying before, to reply to your question, there's a evident pattern of distributing responsibilities across multiple functions. We never have one function that makes a lot of calls or one function where a lot of contracts rely on, because it would be from the engineering extremely inefficient. But we have a lot of contracts, a few functions inside these contracts, and a lot of and the functions call just 1 to 4 contracts. So we don't have a centralized dynamic of calls. And here, these are all different components, and we plot the number of components of each DApp. The color is given by the chain that they are developed. And we see that the number of components is always quite high. So we never have a DApp that is just one component, so all the functions talk with each other. Given that we found out the DApps are quite similar in the way that they are developed, From now on, we consider all the DApps together. And for example, here, we plot all the nodes of all the networks together. Now let's go through this plot.
Can I ask a question before
Sure.
we go to?
Sure.
So for your, can you go one slide back? And so maybe it's also depend of the DApp type. So in some sense, maybe because today you have Avalanche and Uniswap, which both of them, as I see, by structure, want to keep things in one smart contract.
Mm-hmm.
And so for this reason of lending and trading, it makes sense to have one smart contract. However, if you think about Web3 applications that you start doing stuff that are more complex and the contract, it's not really straightforward, like simple functions, then you want to start moving to a different network structure that maybe you have a lot of smart contracts and few functions. Or so I'm just thinking about like if it looks like now because it's efficient, or it looks like that because the type of the activities needs to look like that. It's not it's not something that we want to generalize for any kind of DApps application.
For like in our data set, we have many use cases. Actually, we not have just DeFi, and we found that is a common pattern in all of them, like even games or exchanges or
Yeah, so
NFTs.
if you just look on games, for example, you see the same pattern, like one
Yeah.
smart one. Okay.
Yeah. Like not in these slides, but in the paper, we present the plot for a DApp for each category, and they have all the same structure. And it's a huge result because it means that like developers are sharing knowledge of how to build those, or because it's not said that they had to be like that, so not with zero interdependencies or extremely modular structure. It was not said, but for some reasons it's a trend that is self-emerging. And of course, the efficiency from an engineering perspective is the most likely explanation of the trend. Even because, like, I mean, we all code and we all know that, like, writing small piece of code, small contract, small function, it's easier to find a bug instead of writing just one huge piece of code with everything inside. And like we have to consider that the developer usually have a like software engineering background, so they are probably used to code traditional software, traditional platforms. So they're probably bringing this modular structure from their studies to the blockchain, because it's a result that is common in traditional software as well.
Yeah, I see your point. But also, it's a common knowledge, but also there is the other problem that it's easy always when you want to create a new application to copy
To code.
paste something from before, and
Yeah.
then we have a kind of people maintain the same routine, but not necessarily
Yes.
the best. Yeah,
Yes.
but I see your point. Okay, thank you. I think Robert has a question. Robert, do you want us to unmute you? And Kai did it.
Hey, hello. Can you hear me?
Yeah, sure.
Yeah. So, I have a question about so it seems that you analyzed only calls that are visible like statically. Um, but there are many situations where calls are computed, dynamically on the fly. And that can even be the case internally with smart contracts where, like let's say you have like a modular system, and as you deploy new components you update the address of where like a component might reside. So is that like considered here, or like what impact would that have on your results?
It's actually one of the outlooks that we are looking into, like working with live on-chain data to see how it changes the calls. Because we have the most likely network, but having on data live from the chains means that we can actually have a metric of the functions that are actually called and how they are called, so we can differently weight the links of the network. But it's actually the main outlook of this paper to like implement all these analysis with online data. Thank you.
Okay,
And
thanks.
like I'm actually looking into it. So like if we want to, I don't know, hear via email later, it's fine. Thank you.
Thank you.
Okay, if there are any other questions, just stop me. Okay, so we look in other metrics of this network. Let's focus on the right part, that is a random model. So for each network that we have, we preserve the information of the nodes and of the number of links. And then we build a random network with that number of nodes and that number of links in order to see how in random networks the distribution of some metrics are. We choose two measures to describe the structure of the network that are on the x-axis, the clustering coefficient, that is a measure of the interconnectedness, because it's the number of triangles in the network. And we have between a centrality on the y-axis, that is a measure of centrality and is a measure of the systemic importance of the node, because it measures how many paths go through that node. So for example, here in the top node, there's just one path, but here in these nodes over here, there are many paths. So the systemic importance of that node of this node is of course higher. And these are the two metrics that we use to describe the system. We have that in random networks, there are clustering coefficient varies like in between 0 and 0.5. And between a centrality that are not that variable, so they are like concentrated here in this area. And this is just a scheme of what a random network is. If we look at our network, our actual network, we have that the clustering coefficient, it goes from 0.5 to 1. So we have a very different distribution in how the nodes are linked, how interconnected they are. And the between centrality is extremely more distributed across the possible range. And we notice that if the nodes have high clustering coefficient, they have low between centrality. And if they have medium clustering coefficient, they have high between centrality. This is a scheme of what a DApp, of what like our network of DApps is like. And we have that the nodes with the highest clustering coefficient, like these ones that have a high number of triangles that go through the nodes, have low between centrality. It means that they are not important for the pathways or for the interconnectedness of information. But we have the purple nodes that are the one with highest between centrality, so the ones where a lot of paths go through, that have low clustering coefficient. It means that the function calls in our DApps basically has these disconnected components that are the secondary functionality of the DApp that do not interact with the core. And the core has communities of function that are extremely linked within them, that are grouped by functionality. And we have few core functions that are the ones with highest betweenness, that are the functions that link different parts of the core of the application. Then we know that high clustering coefficient means that they could resemble a small world network. A small world network is a network that has high clustering coefficient and show path length. And it's basically the one here, where we have that it's like a regular network, but there are some parts that are the efficient parts, that basically if we want to connect two nodes that are not directly linked, we can always find an efficient path that connects them. And we have, and that brings a path length that is low, because we always have these extremely paths that go through the network and can reduce the path length of the information. So we already know that the clustering coefficient is high. We compare the average path length. Sorry, yeah, please. I didn't see.
Yeah, so question on the previous slide. Your results also show that the network looks like a hub and spoke network, which seems much more likely than a small world network. Small world network, let's see, if you go back one more slide.
This one?
The real network looks like a hub and spoke network. It looks like everybody goes through, whether it's liquidity pools or staking pools or gas stations. Everybody goes through them, and then I don't know. Each smart contract itself has multiple modules that are very connected between themselves, but it's just a local connectivity. Why? I mean, if you just look at the numbers, clustering coefficient or things like that, yes, it looks like a small world, but there's no reason to think that there's any small world phenomenon in the smart contract.
No, yes, we don't state that it's a small world network. We are because all the traditional software, like JavaScript, a lot of software that are written in JavaScript, they all resemble small world network. They all have low path length, high clustering coefficient, and they have a degree distribution that is a power law. So we like it because we like these developers, we assume being a developer or having knowledge in traditional software developing. So the question was if this small world feature from the traditional ones is brought here as well. But our conclusion is they are not small world networks. So we are just saying that this feature could resemble a small world network. Even the average path length is more or less similar to the ones of random network with the same number of nodes and links. And that's why we conclude that there are strong local interaction, fast information diffusion, but we don't state that they are small world network. We just say that there are some features in common, so we can conclude that the information diffusion is quite fast because of short path length, because of high clustering coefficient. But we say that it resembles traditional project and traditional in the sense of traditional finance project, but like we don't make these strong assumptions to say that they are small world network actually.
So is it correct to also say that these features resemble a hub and spoke network?
Yes. Okay. It was just like a comparison with the traditional ones. That's why we introduced the small world model, because it's been proved that the traditional are a small world model. So we just wanted to see if there are any similarities even in these cases. But yes, thank you. Okay, so we found that the information diffusion is fast because of this reason. So to understand how fast is it, we plot the click size of the distribution of the click size. Now, a click is a subset of vertices that they are all connected within each other. So for example, here we have these 4 vertices that they are all connected within them. and the size of the click is the number of nodes. So here, for example, we have a click of size 4. And we see that across all DApps, we have like more than 10 to the 3 click of size 7, even more of size 8, even more of size 9, almost 10 to the 4. It means that we have a huge amount of big click. So we have a huge amount of set of functions that they are just one step away from another function. So if we have an output or if we have a bit of information that we're interested in one function, it's just one step away to any other function in that click. That is the community that we were saying before. And if we have a bug, that is the other aspect of the story, if we have a bug or a vulnerability, that bug can easily spread across the community because it's just one function call away from all the functions in that community. The third research question was if they're resilient to target attacks. Now, this is the case of Simple Finance, that is Ethereum-based and belonging to the DeFi category. And the yellow plot is for random removal. So we have the largest component and we randomly remove a fraction of node. And as we can see that the component is not affected because the average path length doesn't really change. But if we do a targeted removal, so if we remove the nodes with highest betweenness, we see that after 8% of the nodes, the DApp becomes disconnected. Here I plot X corresponding to 0 to say that the DApp is disconnected, so it breaks in 2 parts and we cannot define an average path length anymore. This result is consistent if we remove nodes with highest degree centrality, so it's consistent across centrality measures. And we are saying that if we are an hacker, we want to attack these functions in order to steal some tokens, we just have to attack the 8% of the functions with highest betweenness, and we break the DApp in other pieces too, to start for, and the flow of information just stops. It means that if we steal token and the contract that checks that everything is okay is in another part, we manage to actually steal some funds. Now, in this case, the DApp becomes disconnected when we remove core functions like safe degrees allowance and withdraw. So it's important to really check this small set of functions that are the ones with highest betweenness. It's not that important to check all the functions to do an assessment of the systemic risk of the DApp. I mean, it's of course important, but it needs to be prioritized, a check on the functions with highest betweenness. And another important aspect is that this case that I presented here is the case where the DApp becomes disconnected further, because on average across all the DApps that we consider, it becomes disconnected after just 2% of the nodes. So the DApps are extremely susceptible to targeted attacks. They can be disrupted very easily with just 2% of the functions. So we can conclude to go through what I just did. We have data on GitHub. We use a tool in order to extract the information on contracts and function of 66 DApps. And then we divide our analysis. For the contract, so we have all the information available, source and target contract, and we build the network and we analyze the network. We found out that the structure is modular, each contract is self-sufficient, and they do not have a lot of interdependencies. For the function network, we have to infer the most likely network, and then we have the network to make some analysis. And now we have to connect, we have many results from a network perspective. So we have to link these results with an engineering perspective or a developer perspective. What does it mean? All the things that we found for a network point of view. So the first question was, is there a common development pattern? And we can state that there is a common development patterns, and it was not obvious given that the developers is a new community, and like we don't know their background. There are for sure no common rules that they are following. So it's quite interesting that there's a common pattern. It means that they are sharing knowledge and they are actually working with each other. The contracts are quite independent. The functions are not. And the functions with highest betweenness are represent the problem of the potential problem of the DApp. The second research question was if the topological properties can be related to the security risk of DApps. And of course they can, because we found out that it's very easy to manipulate data when they go through the bridge that connect different communities. And the third research question was if they are resilient. And we can conclude that they are resilient if we attack randomly. But if we know what to attack, so the critical bridges between components, they are definitely not resilient. So a lot of attention should be paid to these particular functions to start with. All the contracts are always checked like singular, like there are developers that check the stability of the contracts, but like just as a code, and they do not check how they interact within them. So now we know that the functions where they should start to look at for like a review on systemic risk or an overall stability of the DApp are the functions with highest betweenness. For example, here in the DAO hack, the function split DAO, that was the function that the hacker exploited, is like one of the functions that has highest betweenness inside of the DApp. And that's why he managed to steal more than millions of USD. Now, it has like this study can be used by like many point of view. It can be used by developers because now they know where to focus. It can be used by users because we can state the resilience and the security of the DApp overall. And it can be used for a sustainable aspect because we know that the weight of the links are related to the gas optimization. So if, for example, we have a path that has that is done many times, but there's another path that is more efficient, that goes through other functions or through other contracts. I could save gas fees. Now we know what kind of path we can follow.